Hello there. So let's continue with our talks on Chapter 6, looking at reversible systems which reach equilibrium when the two reactions are working at the same speed, and therefore the concentrations of each chemical in the two competing reactions no longer changes. And we've been talking about the calculation of the equilibrium constant to tell us which of the two reactions had been working harder before equilibrium was established and that stalemate came to pass. And we said that we took the concentration of the products from the forward reaction and they were divided by the concentration combined of the reactants. So for our equation here, carbon monoxide reacting with oxygen combining to produce carbon dioxide. The carbon dioxide concentration was taken to the power of 2 because there's 2 moles in the equation. And the carbon monoxide concentration was taken to the power of 2 because there was 2 moles in the equation. We said we've got those two caveats we have to think about. We don't include solids when calculating the equilibrium constant, and we don't include water if there's aqueous conditions, because those aqueous conditions mean more water. And so a reaction that produces or uses up water doesn't change the concentration of water in a solution of water. And we said that if the position of equilibrium was kind of 50-50, a stalemate between reactants and products, we got an equilibrium constant close to 1. The closer, the more of a stalemate things were. If the equilibrium constant was a value smaller than 1, then it meant that we had mostly the initial reactants from the forward reaction. And if we got a K value greater than 1, the bigger the better, the more the concentration of products outweighed the concentration of the initial reactants. And so we said if the K value was less than 1, equilibrium was to the left. That was favoring the back reaction because it's the back reaction that produces those chemicals on the left. And if the equilibrium constant value was greater than 1, then that means that the forward reaction is being favored, or equilibrium was on the right, because that's the reaction that produces the chemicals sitting on the right-hand side of the equation. So we hadn't looked at any examples with real values in. So that's what we're going to do now quickly. So the reaction between fluorine and oxygen to produce oxygen difluoride. The product of the forward reaction is the oxygen difluoride, OF2. So that's put into our equation and it's taken to the power of 2 because there's 2 moles in the equation, divided by the reactants, the fluorine and the oxygen gas. The fluorine to the power of 2 because there's 2 moles in the equation. We then plug in the equilibrium concentrations which are provided for us. So we get 6 molarity to the 2, or 6 times 6, 20 to the power of 2, or 20 times 20. That comes out as 0.09. And so our equilibrium value is less than 1. And we only get a value less than 1 when we've got mostly the initial reactants, the fluorine and the oxygen. So we say that we have an equilibrium position which is to the left, or we say that the back reaction is favored. It's the back reaction which is trying to produce oxygen and fluorine gas. Second one, this one, a combination between carbon monoxide and hydrogen to produce methanol. And so products divided by reactants. Our product is the methanol. Again, this is taken from the point of view of the forward reaction. The reactants, carbon monoxide and hydrogen. The hydrogen concentration taken to the power of 2 because there's 2 moles in the equation. With the expression set up, we can then plug in the concentration values, moles per litre, which have been provided for us. And so that crunches down to a value of 14,400, or 1.4 times 10 to the power of 4. It's a value much bigger than 1. And so we've got mostly, as we can see from the calculation, mostly the products of the forward reaction produced. And so the equilibrium is said to be on the right, or we can say that the forward reaction is favoured. It's the forward reaction which is trying to produce this methanol, which is in such great yield, 90 molarity, compared to the piddling amounts left of the carbon monoxide and hydrogen. So the forward reaction has been very successful once equilibrium is established. Take a look at a couple of quick practice problems. So write the equilibrium expression for the reaction here, which we'll do so now. So remember, the expression for the equilibrium constant is equal to the combined concentration of products from the point of view of the forward reaction divided by the combined concentration of reactants. Our products are hydronium ions and bromide ions, and the reactants are hydrogen bromide and water. Remember our caveats. We don't include solids, but there are none here. And sometimes we don't include water. We don't include if there are aqueous solutions, which there are. So those hydronium ions are in a solution made up by water as the solvent, and those hydronium ions are surrounded by molecules of water. Same with the bromide ions, which are aqueous, surrounded by molecules of water. So a reaction which uses or produces water isn't really going to change the concentration of water when we've got these aqueous solutions. So we do not include the water. So, whoops, give myself some room here. So it's going to be the hydronium ion concentration multiplied by the bromide ion concentration divided by the concentration of the hydrogen bromide itself. So if we had a value for the equilibrium constant of 4.2 times 10 to the negative 3, that's a value less than 1. And we only get a value less than 1 when we've got mostly the initial reactants. So that means the equilibrium is to the right. Sorry, I beg your pardon. Equilibrium is to the left. Still half asleep this morning, I guess. Because it's the back reaction, the reaction from right to left, that produces hydrogen bromide. That's the only way for it to be in relatively high concentration. So the concentration of the hydrogen bromide would be high. The concentration of the hydronium ions and the bromide ions, which are being used up in the back reaction as we move from right to left, concentration of the hydronium ions and bromide ions would be low. Any reaction uses up its starting materials when it's being successful. The next one, an equilibrium constant of 8.91 times 10 to the negative 4. That's an even smaller value. So equilibrium is even further to the left. The back reaction is even more favored. So we have an even higher concentration of the hydrogen bromide and an even lower concentration of the hydronium ions and bromide ions. We're not sure quite what the value is. We'd need to have equilibrium concentrations of these chemicals for that. If the equilibrium constant was 6.05 times 10 to the power of 3, so an answer much bigger than 1, This only happens when the position of equilibrium is moving from left to right. We're favouring the forward reaction. For a value greater than 1, we need lots of these chemicals and very little of this chemical. So equilibrium favours the right. The forward reaction is favoured. So we've been using up the hydrogen bromide rapidly. Its concentration will be low, and producing the hydronium ions and bromide ions, their concentration would be high. That's a rubbish arrow, to be fair. There we go. Let's take a look at Le Chatelier's principle now, which explains how we can predict the response of a system when a change is being forced on it. Le Chatelier tells us that a system responds to compensate for any changes. So imagine your chemicals were all finely balanced on a set of scales, and we decided to add a chemical, getting ahead of myself there, add a chemical like carbon monoxide. So if the scales were finely balanced and we suddenly added more weight, more carbon monoxide, it would tip the scales as shown. So if the system was going to address this and regain balance, it would have to shift that balance from left to right. We'd have to take some of the weight on the left and move it over to the right to regain balance. And this is what the system does. When a chemical is added, we effectively move equilibrium away from that chemical to compensate and regain parity, regain balance. That gives us a first rule for Le Chatelier. Whenever a chemical is removed, move equilibrium away from that chemical. Now in this instance, moving away from the carbon monoxide means moving from left to right. So we can say that equilibrium moves to the right, and we can say that the forward reaction is favoured. That's the job of the forward reaction, using up these chemicals and producing these chemicals on the right. We can also understand this from collision theory. We add more carbon monoxide, there's going to be more collisions with molecules of water. And so the rate of the forward reaction increases, and that causes a shift to the right. So adding a chemical moves equilibrium away from that chemical. That's our first law for Le Chatelier's principle. Second idea is removing a chemical and how will the system respond when a chemical is removed. Well, again, imagining our scales, we've got the two sets of chemicals balanced either side, and when we remove a chemical, it's going to make that side lighter. So the response of the system when one side is too light is to redistribute the weight, move across to the side where the chemical was removed, so we can regain balance, regain equilibrium. And so this gives us a second law for Le Chatelier, which tells us when a chemical is removed, the system compensates by moving towards the chemical. Add a chemical, move away from it, remove a chemical, move towards it. And so for example here with the chemical removed on the left, we'd have to move from right to left. That's a movement to the left overall, is favouring the back reaction. And again, if we think about collision theory, we can understand why that is. Removing the chemicals on the left, let's see, was it water? Yes. So removing water means that there are going to be less collisions with molecules of carbon monoxide. because the water concentration is decreased. Remember, it's water in the gas state, so there's no solutions here. So removing water is significant in this example. So we've got fewer collisions with molecules of carbon monoxide. The number of collisions decreases between these chemicals, and the rate of the reaction slows down. But that's specifically the rate of the forward reaction, which depends on collisions between these chemicals. We have not affected collisions between carbon dioxide and hydrogen because we didn't remove or add those chemicals. So the back reaction is still taking place at the same rate initially. It's a forward reaction which slows down, and so the competing back reaction starts winning and moves equilibrium in its direction to the left. So adding a chemical, we move away from that chemical. Removing a chemical, we move towards that chemical. Our third and last idea for today's lecture is when we add a catalyst to the system. Remember, we said in collision theory, adding a catalyst lowers the energy of activation, so more of the collisions have the energy of activation and the reaction is faster. Now that's still true, but as we look at an energy diagram with that catalyst effect, we can read the diagram as we normally would from left to right to represent the forward reaction, but we can also read the reaction from right to left for the back reaction. And so for the back reaction, we'd normally put in this much energy for effective collisions, but now we only have to put in this much energy for effective collisions. So the addition of a catalyst in a reversible system has lowered the energy of activation for both the forward and the back reaction. And so the equilibrium system is still a tie. It doesn't change the position of equilibrium or the concentration of any chemicals by adding a catalyst. We just reach that equilibrium point, that stalemate, faster. Catalysts will not affect the position of equilibrium because it lowers the energy of activation for both the forward and the back reaction. Okay, let's see what else we have to do. Anything? Oh, a couple examples to finish off. So our first one, adding acetylene. If we add acetylene, let's find it in the equation. There it is there. We said we add a chemical, we move away from that chemical. So equilibrium would move to the right. We'd use up more acetylene as we add more because there'd be more collisions, and we'd turn it into the product, ethanol, faster. So equilibrium moving to the right, the forward reaction favored. Second one, with iodine being removed, there's our iodine there. We remove a chemical, equilibrium moves towards that chemical. So that's a movement from right to left. Equilibrium is moving to the left because the back reaction is favored. We've removed the ingredients that drive the forward reaction, and so the back reaction is winning for a period of time without the forward reaction competing fairly with it. Remember, we do eventually recover that equilibrium because as the back reaction works harder, it produces more of the iodine, replacing the chemical that was removed. Remember, that's the whole idea of the Chateliers Principle, compensating for the change. We add a chemical, we've got too much, so let's move it up and move away from it. Remove a chemical, we've got too little, let's move towards it and replenish that chemical that was lost. Third one, sulfur trioxide being removed. So we find sulfur trioxide in the equation. There it is on the right. So we remove a chemical, we move towards the chemical. We're compensating as we move equilibrium to produce more of it. Forward reaction favoured when the sulfur trioxide is removed. And lastly, adding more dichlorine pentoxide. Kind of weird how I've got it set up here, but never mind. Let's see, look for the dichlorine pentoxide. There it is there. We add more. Equilibrium realizes that we have got too much, so we move away from that chemical, favoring the back reaction as we use it up in the back reaction to produce more chlorine dioxide and oxygen gas. Okay. Anything left? No, slightly out of sync here. There we go. So one last page of examples before we finish. Let's see, and again, you can always pause the video and think about these questions before I answer them. Okay, so which reaction is affected by adding more oxygen gas? So adding more oxygen gas, there it is in the reaction. It's one of the fuels, along with nitrogen, that drives the back reaction. So the back reaction is the reaction which is going to be affected. So how does the system compensate? Well, if we've added too much, we have too much, equilibrium moves away from that chemical. We're moving from right to left to compensate for having too much. We're moving in the direction of the back reaction. So we can say that the back reaction is favoured. We move from right to left. That's a movement favouring the back reaction. We can see why when we think about collision theory. Add more oxygen, there's a greater concentration, so there's more collisions with nitrogen, and so the rate of the back reaction speeds up. So what happens to the concentrations of nitrogen and nitric oxide? Well, if we're moving to the left, we're using up the oxygen and nitrogen, so its concentration will decrease, but we're producing more of the nitric oxide, its concentration will increase. That's always a consequence of a reaction working harder, uses more of its starting materials, and produces more of its product. So that's the first one. Let's finish off for this morning. Squeezing this in before my baby girl wakes up. So explain what would happen to the position of equilibrium if the volume of the solution was doubled by the operator. So we've got ammonium chloride, a solid, which decomposes to give ammonium and chloride ions in solution, aqueous. So ammonium and chloride ions are part of the solution, while the ammonium chloride is not. So increasing the water, doubling that water concentration, will halve the concentration of these ions. It's like adding more water to dilute your orange juice. Dilute to taste, that's it, dilute to taste, it decreases the concentration of orange, and we're decreasing the concentration of these ammonium ions and chloride ions by adding water. So that dilution by adding water feels like, for the ammonium and chloride ions, it feels like we are removing chemicals when their concentration decreases like this. There isn't really any change in the total amount of chemical, but we're tricking the solution, tricking the reaction into thinking that we've removed chemicals by diluting their concentration. And so Le Chatelier tells us when chemicals are removed, we move towards the chemical removed. So to move towards the ammonium ions and chloride ions, this is a move from left to right, favouring the forward reaction. Or we can say that equilibrium moves to the right. That's it for today. That's certainly enough to be thinking about for today. So we'll come back on Wednesday. Remember, that's the actual proper online lecture for section 1. No lecture on campus on Wednesdays normally, before coming back to campus on Friday to finish the lecture and finish the chapter. On Wednesday, we'll talk about energy in reactions, which we've already touched on when we talked about the catalyst effect, because we can read an energy diagram from left to right for the forward reaction, but we can also read the energy diagram in reverse as we read an equation in reverse as an interpretation of the back reaction from right to left. And that changes the amount of energy required for effective collisions. And we find that with these reversible reactions, one of the reactions will be exothermic, giving out energy, as the forward reaction is here. And one of the reactions will be endothermic, putting in more energy than it gives out. It changes whether the exothermic and endothermic are the forward and back reaction, depending on the particular system you're looking at. So we've been thinking in terms of how temperature changes, increases and decrease, favor a particular reaction, exothermic or endothermic, but more about that on Wednesday. Stay safe, wash your hands, wear that mask.